All right, great. So we're going to start the second half of today. So as in the second half, we have a few goals. One of them is in the first half, we covered like BERTs, Roberta, basically, and I showed you how to do that with Hugging Face. In this second half, we're going to look at GPTs. So that I have another example of the GPT example. This actually is in the context of reinforcement learning through human feedbacks, although it's a massive topic, so we're not going to get into that just yet. We're going to, the very basic thing as we did with the BERT of just doing something with it. Very simple. But you can see it's already, that same approach is being worked into RLHF as well. Okay, and then the other thing we'll do is just at the end of, towards the end of the class today, I'll set up the Anaconda environment, and we will create an environment, do the pip install of a couple of libraries, and hopefully get one of these to work on your computers. I tried this on my CPU and it worked fine, so we may need to wait a couple of minutes, hopefully, not more than that. Remember, we are doing inference here, not pre-training or fine-tuning. So there's like a distinction there that you have to think about. There's three things that you can do with these transformers. You either pre-train, which is massive, and pretty much outside of, I mean, you can do pre-training, you will do it for a homework assignment, but your model will just not be of the quality of even GPT-1. I mean, it's not gonna, because you would need way more data, more computing power. But you can do it, certainly. So, but that's the most resource intensive, GPT. And then, pre-training. And then fine-tuning is something we can do in this class, but it's the thing that on a CPU overnight, right? Or if we have GPUs, it can still take a little bit, right? So it just depends, but that's a very realistic thing that we can do and have nice models. And then there's the inference part. And inference just means whether we have a pre-trained model, BERT or GPT, or we have a fine-tuned model, BERT or GPT, but we're just using it, right, to predict. So we're not updating the weights. In fact, we're just giving it inputs, getting outputs, right? That's basically what we've been looking at today. All right, so the next thing I want to discuss is now a GPT model. So here, this is already linked. So I just clicked on, I went to table of contents. Okay, and I clicked on the RLHF module, and I have several examples in here. The one that I'm running currently is the general pipeline for RLHF. Okay, so I remember I'm still working on that example where I want to build my math GPT. All right, so I need to start with a pre-trained GPT. So in this case, I'm going to take the Hello World GPT, as I said, which is GPT-2. Okay, so we'll try to get this to work in a sec, but let's just discuss. So I clicked on this link here, right? And I can click on it again. All right, and it opens the Jupyter, which is in my transfer learning repo. And so now you can see, I have everything in here. This is actually for we won't do this today, all of this, but it does have the familiar pipeline from transformers, etc. Okay, so again, you can disregard all of this because this would be for the RLHF, but we're just going to look at the simple example of bringing into this code our GPT-2. So there it is. The model is GPT-2, right? So you're trying to build your math GPT, that's your entrepreneurship, whatever you want to call it, or your research project. You need a pre-trained model, and you're going to fine-tune it, okay? So we're not going to do all of that today. We're just going to look at how to bring in the model. But the idea here is to take a GPT, such as GPT-2, a better model would be Llama or Llama 2, right? And fine-tune it with a technique called RLHF to be better at performing a task, such as providing answers given prompts, right? So that can be a lot of things. So for instance, I've made it even more generic or more specialized than just asking questions and getting answers. I said, I want to build one that solves high school level math problems. But if you think about it, it's the same idea. I'm going to give it a problem, get an answer. That's equivalent to asking a question and getting an answer, right? Because I'm fine-tuning it for that specific task. So really, what's the only thing that changes? The data. The procedure is the same, right? So I can, let's say I want a GPT that's really good at answering political questions, and you give it questions and answers about politics. If you want one that solves high school level math problems, you give it a math problem, you get an answer. If you want one that's really good at physics, you give it physics related things. So really the same technique can be used, and all that's changing is the data set. And you can literally build, you know, these fine-tuned models. All right, so first we need the GPT. So here, you know, we're going to use GPT-2. Of course, we are using Hugging Face here. So we're using their transformers module. So we use their functionality. Once again, very familiar, the pipeline. Very nice. Now, we don't always have to use the pipeline. We can do things a little bit more from scratch because remember, all this is code wrapping. So they have one version, and then they have one that wraps around other versions. So they're very efficient that way. All right, in this case, in the previous one, what did we do? Mask, fill in the blank, right? Something like that. Here, notice that pipeline has multiple things that it can do, such as text generation, okay? And so now we provide a model that makes sense, in this case, GPT-2. This device just means, this is a familiar thing in PyTorch of CPU, GPU, that kind of thing. Notice over here then, what do we need? We need also the tokenizer. I already explained what this is. All right, so from auto tokenizer, from pre-trained GPT-2. As long as these two names match, you're good to go. But that's not all you can use. I mean, you have, let's say, J Shapiro / my very intense GPT, right? So he can have one that's like a GPT, and you can download that one. As long as he follows all the Hugging Face requirements, you know, you can, like I said, you can create your own accounts and have your GPTs in there as well. So there's a lot. I've not counted how many models they have, but there's a lot. Think about it. It's the whole world using this thing. All right, so yeah, so I have a pipeline. I know that I'm going to do text generation. You define a few things, like what is the padding token? And if you remember, we talked about padding in 520, but it just has to do with when the sentence does not fit into the defined size of the vectors that you give the model. All right, and so these are some calculations for the RLHF, so don't worry about that. You really just need the tokenizer in the model. And now, before fine-tuning, which is all that we're going to cover today, you want to try out your GPT-2. Okay, so you can see here, you're going to give it a prompt. Now, it takes a list of prompts. So what that means is you can give it actually 50 sentences, and it's going to give you 50 answers for that. So it's like you give it 50 prompts, and it's going to give you 50 text generations. Does that make sense? Okay. And I think I have an example of that as well. And that's basically it. Hugging Face then makes it really good. You have generate examples is the generate examples is what here? Model GPT generator is the model. Generate examples. Is that a function that I imported? Oh, yeah, I'm sorry. Yeah, it's a function that I define here. I forgot about that. Okay, so there's a function in here called, in the utility functions, I have this function called generate examples. Here it is. Okay, so there it is. So it takes the generator, and then it's going to iterate through the list. Yeah, so this is what I was saying. So this is actually what does, where you can take a list and generate all the answers for the list. So as you can see, it's doing for prompt and prompts list, Then we take generator, which is this one over here. This is prompts list. And now we're running the prompt, the max length. So actually, Hugging Face does not provide that. This function is actually how I got it to work. All right, so, and then once you have that, you generate basically the results and you print out everything. Okay, so we can use this function for that. But now going back to our example, here we have, how is the weather? That's the list of the list of questions, actually. I should have written the question there. And then model GPT generator goes through this function and it says something, okay? So in this case, as you can see, we tell it, how is the weather? And it gives answer 1 and answer 2. Why answer 1 and answer 2? Because remember, this is for RLHF. So what we want to do is eventually we want it to generate one answer and another answer, and we're going to say which one is better and which one is worse. And this is how we're going to fine tune it. But again, don't worry about that for now, because that's a slightly more complex thing. But the idea would be that as we're trying to make the math GPT, we would give it a problem, the high school math problem, and it's got this answer for that math problem, but it also generated this answer for the math problem. You see that? In theory, one is better than the other. Would you agree? Would you agree that that's a good assumption? They are different, right? So if they are different for the same math problem, would you say that one might be better than the other? And then you don't, in theory, if we think as humans, we would say, I would read one and say this one is better than the other, but we can't have a human do this, right? Because that would be too intensive. So instead you create another neural network that basically takes that input and assigns a number. And it needs to, that function needs to learn to give numbers that favor good answers versus bad answers. You see what I'm saying? So RLHF involves two neural networks. The GPT, there are two transformers, actually more, but at least one transformer that generates the text and another transformer that reads the generated text and assigns a score from 0 to 1. But how do we train that one to do that? You see that? So that is done by having humans generate the same data, and then we train on it. Anyway, that's RLHF. I don't really want to get into that just yet, but that's kind of the underlying idea. So in this case, this is why this is generating two answers like this. Any questions? Now I'll make one comment here. I haven't read this text. Remember, this is coming from GPT-2, which was trained on the internet. You may encounter when you're reading this kind of text sometimes in the examples, foul language, bad words. There's a lot of toxicity, as you guys have heard, on the internet. So unfortunately, I apologize if that's something that's offensive to you guys, but it's the nature of the beast, basically. As we are dealing with GPTs, we are dealing with models that were trained on the internet. And on the internet, there's a lot of trolls, right, that are basically saying a lot of bad words, using bad language, and it has learned about that. So this is a common issue that at some point I will talk about it. We are actually creating this is kind of a side note, but we're here in the department, we're creating a master's in AI, and one of the courses will be like ethics in AI and that kind of thing. And it's because it's a serious problem. So there's bias in these models, so we'll talk a little bit about that. There's toxicity in them. They can be very offensive sometimes, but that's a representation of what they learn, which is the internet. And if you've ever gone to 4chan or something like that, it's awful. Okay, so I'm just saying that can happen. Okay, so just be aware of that. So that's kind of a side note because it is an important topic. And it is a topic that is being addressed in AI through ethics courses and things like that. But it's not an easy thing to solve. And although there are ways of trying to address it. Okay, anyway, so that's the example. That's as far as I want to take it as far as today, right? I don't want to get into such a complex topic as RLHF because that's more of a overarching through the whole semester. We'll be coming back to it and it'll make more sense a little bit every time. I do believe I have another example. Oh, he left already. But someone asked the question of the fine tuning, right? So how does that work? I have a GPT, and then what is it that's being fine tuned? So here's actually the example of that. This is another GPT-2 model here. And if you notice, what do? You want to, let's say we're talking about this reinforcement learning reward model, the one that I said reads and gives a score, right? It wants to learn from the human feedbacks, which were actually humans rating solutions to the problem. So the reward model starts with a GPT-2 and adds a head. A head is just, if you remember from 520, we did this all the time, add a linear layer. Takes whatever the output was, which was an embedding, but now the neuron that comes out is different. Okay, it might be the size of vocabulary, it might be a score, you can do whatever you want. So we'll come back to that later. And it learns to predict scores based on ratings. However, as we are gonna begin to fine tune this model, we need to freeze some layers so that only certain weights are updated and others are left as is. So if you notice, this is the model here, and now we say that we want to freeze the first 70% of the hidden layers of the reward model. So in PyTorch, that's straightforward, or in transformers, that's straightforward. You just grab the model and then you say .transformer.h, that gives you the number of layers, which I think is 12 for this example. And then, I printed the number actually. So 12 layers. And then you take like a percentage. So you say, I want 0.3 of them not to be frozen. Okay, so then what do you do here? 4 layer in layers, from 0 to 9. And we're going to, and the key thing, remember this one requires grad. We saw this in 520 a few times, right? It basically meant that we wanted to turn on or off that switch that allows you to update the weights. Yes or no? Okay, so here we're going to say that we iterate through all 12 layers, and we're going to say which ones we turn off requires grad and which ones we leave it. And that's it. That's how you freeze the layers. This is a very common practice. And then just to check which ones were frozen, I kind of just iterate it through all the layers again. And you can see here, layer 0, layer 1, layer 2, layer 3, layer 4, layer 5, 6, 7, 8, 9. Notice that for all of the ones from 0 to 9, the flag is false. Do you see that? False, 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 false. When we start to get to layer 9, they start to become true, right? So I believe 8 ends here. All the parameters basically are not updatable. That is a desirable thing, right? And then the last 3 layers of the GPT get a true. They will be changed. That's it. You don't have to add more layers. Could you? Yes. Definitely. Right? You can do whatever you want, right? But in general, now think of how this works, right? So you have a transformer, which you have an input, right? So you have the input going in, you're going through all the layers, and then you got the output. The way that you want it, why the first 9? Why do we freeze the first 9? And then we leave the last 3 so that they can be updated. What's your intuition there? Yeah, please.
First parts were trained.
But the first 9 are frozen. So it means it's like they were pre-trained. Those weights are set in stone. That's what I'm saying. So it's like, take a transformer, right? And we know it's a neural network, right? Layer, hidden layer 1, hidden layer 2, something like that. So I'm saying that the input goes in and the weights stay exactly the same as this GPT-2 that we just downloaded. But after layer 9, 10, and 11, and I think 12 is the last one, I think, or 11. Yeah, probably starts at 0. And so those, as we fine tune, those weights will be changed. So why do you think that is? What's the intuition there?
So for say our base model is predicting the car, bus, all the vehicles. And our model, we just want it to predict if it's a car or a bus.
Mhm.
First layers, first few layers, they will be much more useful, and then later we can just filter out and get only those layers.
Yeah, I see what you're saying. Yeah, so exactly, that makes sense, right? So it's basically, we're taking, in this case, we're taking text. And we just want to, it's almost like, although this may not be what's happening, you might say, we take text and the first 9 layers already learn that that's a noun, that's a verb, that's a determiner. That's actually something related to sentiment. That's actually related something to trees. You know what I mean? It already learns in those 9 layers how to read those text inputs and take them to a certain embedding, right? That has captured some semantic information in it. But then after that, that semantic information needs to be used for a specific task, such as solving math problems. So then it's like maybe you get a lot of data in the embedding at layer 9, but some of it is very math specific. And so now that needs a few layers to kind of read that and convert it into the thing that you want. Do you see that? So it's almost like that. A good example of this in CNNs is like ResNets. ResNets take an image, run all the filters, remember? And the filters know how to extract things about the images. Like these look like eyes, these look like eyebrows, so then that's a face. But our problem is to detect faces of children in trouble. So what do we need? We need the first 9 layers just to take an image and tell us if there's a face in there and that it is a face. And it's a child even. But then the last 3 layers is where we fine tune it to tell us, okay, that kid is in trouble versus that other kid. Does that make sense? So that's kind of a good intuition. So here, did someone say something? Here, ResNets, which is a similar solution with CNNs, is very intuitive. Okay. Yeah. All right. So anyway, so he left, but that's actually one of the things I was going to show you is how you do freeze the layers. So this is part of the fine tuning process. And then I think I have this last example here where I gave it a list of prompts, right? So this is, you know, what is the latest news on the stock market or something like that. It's any question you want to give it. So this, I don't remember the number, but it's some. And again, we use that our handy generated samples function. We give it the model GPT generator, the prompts, and then it generates examples. So this is, I didn't want to print all of these because it takes a lot of space, but I printed out one. Okay. And that's the answer that it gave. So it says, what is the latest news on the stock market? Answer 1, what is the latest news on the stock market? We've got you covered. Bloomberg inflation for March 2013 is 2.4%. A quick look at the chart. And this chart shows that for the last 3 years, the US stock market hasn't been rising more than 1%. What do you think about that answer? Huh? Is good? That's your opinion that it's good? Okay. All right. There you go. And that's GPT-2. So think what GPT-4 can do. Now think what ChatGPT can do, because ChatGPT has been fine-tuned to provide even better answers, right? Because people have rated how to answer these questions. I mean, for the example, for OpenAI, they basically gave these questions to people, and people would say, this is the answer, or this is the answer. And then they would do this selection of which one is better, and they would train the model on that. So the model basically learned how to answer like people answer. Okay. Questions? Yeah, please go ahead.
I think all the answers do not correspond to the question model.
Yeah, that's a good one. I think one solution to that might be that still you want to rate which one is better than the other. Because by doing that, the weights get adjusted more for the one that makes a little bit more sense. So in the next iteration, you get 2 again, and you rate one as better than the other, so the weights get adjusted a little bit more. Hopefully, by doing that iteratively, what might happen is reasonable to think is that after doing that many times, by the 100th time, you get an answer that's actually good. You see that? It's a thing of you don't know the final outcome. It's more like you're always nudging it a little bit. This one is better. That one is better. You see what I'm saying? And you keep doing that, keep giving it data. Eventually, the magic is you get a good answer. I'll give you another. So this is kind of what I wanted to show. Then I'll just talk a little bit more about RLHF in general, and then we'll start a little bit of the coding, okay? So the next thing I want to talk about is the actual, I've mentioned RLHF a lot, right? So there's an actual original paper for the idea of RLHF. It wasn't actually created for GPTs or this kind of thing. It was actually done for games. So reinforcement learning has lived a lot in the space of games. So in this class, we'll cover a game. We'll do reinforcement learning to play a game called Frozen Lake, which is very easy 2D game. In reinforcement learning, there's two main techniques, Q learning and PPO. So Q learning is one, you maybe have heard of deep Q learning or AlphaGo or some of those models. So they were based on Q learning. But there's also PPO, which is actually what the GPTs are based on. But anyway, the original idea came from this problem, okay? So you had to create these games. And in a game, you know the rules of the game. You play chess, you play checkers, you play, Atari games, whatever it is, you're always, you know the rules. So you know when you did good, you did bad, you get points, which are called rewards, right? So you get a reward for killing the queen or the knight or the rook or something like that, right? This is established in the game. So it's kind of easy to create an environment that provides these rewards because it's based on the rules of the game. And so they do this in Atari. That's a state of the art. So you have now neural networks that can play Atari and win, right? So that's done. AlphaGo, the game of Go is like a game in Asia that's really like difficult, much more difficult than chess. And this game also, there's a human player who was the master from South Korea, I believe, and they were beaten by I think maybe OpenAI or deep learning or DeepMind, sorry, created a model, and now they were able to defeat the world champ. So if it's a game, great, but how do we take that to the next level? This is the question that the people in reinforcement learning were thinking about, not even thinking about large language models or NLP or anything like that. So they were just thinking about games. And so they maybe, to make things really easy, decided, okay, instead of having a chess match where we know the rules, or Go where we know the rules, let's actually build a 3D engine. Let's have a humanoid or a robot, and let's teach this humanoid or robot how to dance salsa. The dance. You see that? That's not a game, right? How do you teach a robot or a humanoid robot thing to dance salsa? Where do you get the rules for that? How do you know that, you do some move and that's good and another move? How do you know this is salsa and that isn't? Or how do you know this is good salsa and this isn't? You see what I'm saying? So creating the rules is difficult. When you're creating rules just for games is very difficult. Now imagine for something as abstract as teaching a thing to dance. So as they were thinking about this problem, they came up with the idea of reinforcement learning through human feedbacks. So the idea was that they have a simulator where they have this humanoid thing learning how to dance, and they just tell it dance salsa, which basically means randomly move your arms and legs, And so it started doing that. But here's the trick. The reinforcement learning through human feedbacks means that every now and then it would record a sequence of moves that it did, right? And then it would record another sequence of moves that it did, and then it would record another sequence of moves that it did. Those three little clips were then, let's say after 1,000 iterations, they're displayed on the computer. So you got this video, and this video. And now a human will look at one, look at the other one, look at the third one. And all they have to do is say which one is best. I think this one looks like salsa. Click. And then that happens for a while. And then again, 3 choices. I believe in their paper it was 3 choices. If you notice, it's here is only 2. And so they would give 3 choices again and click and click. And you don't have to do that every iteration. You just do it every few iterations. In the background, you have the model that's generating the moves, and you have another model that looks at the clips and needs to say which one is best. You see the trick? Now, this model initially looks at the 3 and randomly assigns values because it hasn't been trained. But over time, as you get humans to every 1,000 iterations, click on which one is best, you have training data. And so you will use that training data to train the reward function, whose only job is to look at the 3 clips and say which one is best. And it's learning from the fact that a human was looking at them and clicking. Do you guys understand? So that was the original paper. And then, of course, OpenAI adapted this idea to text in the way that you're seeing here. So I think I had the example up here, right? So you give it a question, how is the weather? And then it generated 2 answers. A human looks at both, reads them, and says, this one is better than the other. And OpenAI hired some people, did 100,000 of these. People rated which one is best, which one isn't. And then they trained the model, a second neural network called a reward function that learns. I read this text and I'm going to say this is better than the other. In theory, that, or actually not in theory, but in reality, that allows the model to learn how to dance salsa because, as I said, it's moving randomly, but as you say, this was better, it knows what those weights were. So it's going to give a lot of emphasis to those weights. You see that? And then the weights continue to get adjusted according to this training data. Do you guys understand? Is it clear? All right, so the original idea came from that, as I said, from dancing salsa, and then it was adapted, obviously, to text. But basically, you have the 2. This is actually like GANs, right? If you remember in GANs, we've talked about this already. We had a generator and a discriminator. 2 neural networks giving feedback to each other. This is similar also. You have a GPT or a simulator generating stuff, and then you have something else saying which one is best in this case. So in the GANs, you say it's real or fake. In reinforcement learning through human feedbacks, you say of the outputs that you generated, this one is better than the other. And then the weights get adjusted accordingly. Okay, so that's basically, it's still training, right? So that's how it's able to train. Any questions? All right, so hopefully that makes sense. That's kind of where we are right now in the state of the art of this. This will be a common theme that I will use because it basically covers everything. But we'll just drill down to specific things as we move through the course. All right, so in the next section, what I'm going to do now is just we're going to start Anaconda. So hopefully you have your laptops, you can create or download Anaconda. Should be available on the desktops, I believe, so you can also just start it up. I'm going to stop this video and create a new one so it doesn't get too long. And then I'll just kind of demo this GPT, and hopefully we'll get it to say something, okay? I won't assign a homework this week, but your homework should be that you don't have to submit just to get Anaconda going and get a GPT or a BERT to generate text, okay? Just to get to practice those. All right, so let me stop sharing here. I'm gonna end this one.